Okay, we were more or less here. So let me try to say in simple ways how this computation are done. So you have something like this. So I recall what is this, and then in a second you will see more in detail. So these are Gaussian measures in this way because these are fermions, so it's not positive definite. This is instead just a Gaussian integral. So you have this a Gaussian integral for the bosons, let's say this for the fermions, and these are sources, so you can forget for the moment. This is the generating function. So the correlations are obtained making derivatives of this J, of this eta, and so on. So you can forget. I mean, this is just field. What is important in this piece? And then now at this point you can say we can integrate the Z, and then we will get a classic theory. Okay. So this if you I recall you what is this? This was the aim for this part of the talk is to describe how you compute, for instance, the correction of the geomagnetic factor. So as I told you yesterday, yes? Yes, this is the field. Yes, yes. This is they're completely different. This is the field. This Z is it's a constant. It's the field renormalization. So these are the bare quantities. You have to fix this Z, so or this parameter is like this. This is the wave function normalization. This is the bare mass. You remember in quantum field theory you need the bare quantities. So this is the bare mass. This is the bare wave function. Yes, and eta also is an external field. So J is the external field for the current. Eta is the external field for the field. So this is the generating function. So if you make derivatives of this, of the log of this, then you will get the control-theory correlation. Okay, but for the moment, but the important part is this. So this is the coupling, this is the field, and this is the Fermi. Lambda is the coupling. Is the coupling, which in reality is something like alpha. Yes, lambda S is plus or minus. So lambda, because we need an expansion parameter. So this lambda is because I want to connect this with the formula. Now I have to go to first page. Maybe I say this. No. You remember I started from this. I want to find the result found in physics, right? So. I'm discussing the neutral sector of the correction of the geomagnetic factor. And the result of, I wanted just to show what is the lambda. Okay, this is the result of Jackie and Weinberg of the 72, and lambda should be okay, anyway, these are parameters, okay, so anyway, alpha should become here. Lambda is connected to alpha. Alpha is the Weber. It's Cabib. No, Cabib is Weinberg. It's the angle of Weinberg. Then the angle of Cabib is for lambda. Okay. So what I want to do, so as I said, that you consider this is the result in formal perturbation theory at the first order. Then if you go on, you need a normalization and so on, so you cannot bound. So I want to find a regularized functional integral which gives you this up to correction which I can bound, because I want to do something non-perturbative. Okay. So let's go. So at the end, but so if you want to see this in the usual, here is a more clever way. Yes. So this is what I just understand. It's important to say that this object has cutoffs. Okay, so this is the difference respect to the formal treatment. So it's Euclidean first, and then there is cutoff. So this is the cutoff. So there are a lot of cutoffs because so this is the propagator, right? So but when k is equal to 0, it's not 0 because there is the mass. Then maybe we can remove it, but for the moment I put it. There is the mass of the boson. It is not this is not an unphysical assumption because this is the reason why I'm studying the Z, because the Z has mass. It's like the photon with the mass. If you want, but with the mass. And then you have a cutoff key. This key is a function done in okay? It's better. Yeah. You could say why it's so specific. Okay, because in physics, usually people use Wilson uses the key function. So, but the key function, the Fourier transform is not good. Right? Then you could say, well, then let us use an analytic cutoff. Analytic is too much, would be smooth, so it will be so pathetic. So the best compromise is compact support and smooth is Vieri, which is infinity, but what we believe is that the result is independent on the key, of course. But for technical reason, it's the best stuff. So, of course, all the point from the physical point of view is that the physical result must not depend on the cutoff, of course. So we say this cutoff will be realized in reality by everything, I don't know, gravity, string, loop. And then that's it. We don't know, we don't want to know. Then we put the cutoff at a certain area. The result must be independent on that. It's like statistical proof. Okay? So these are the bare quantities. This is Z, and then S is plus or minus because you know it's the chiral index. So this time is possible. I was in doubt of what to choose, and then I used what to use. No, it's better to use 1, 2, 3, 4, and then this doesn't seem to be all right. Okay, so that's it. So these are Pauli matrices. So these, of course, are so you could, okay. There are a lot of details. For instance, you could consider strange that you have a different wave function orientation for the plus and minus components, but that is due to the fact that this interaction is chiral. Chiral means that this lambda depends on x. That is the famous discovery of Young that weak interaction does not conserve parity. So that is a complication we could avoid mathematically, but I wanted to consider a realistic model, so I put really consider physical one. Okay, that's it. So if you integrate the Z, so this is the definition of this momentum cutoff. So it's a rotational invariant, infinity, Vieri, and so on. And then there is also a finite volume, which you want to remove, periodic boundary condition. At the end, what is possible to do is to send L to infinity. The infrared problem can be solved, but not the ultraviolet. But then the point is that we want to stay at the energy far enough. Okay, now these are the definitions. Maybe I can tell you later. Okay, this is also important. So I don't want, of course, there are a lot of parameters, so it's a bit confusing. On the other hand, quantum theory is complicated. So the physical conditions are that small m is the the mass of the particle, of the electron. Large m is the mass of this boson. So physically, this is small, lambda is small. And then also you have to assume that the cutoff greater than m. And also lambda is greater than this m over n. So this typically is 10 to minus 6, and this typically is 10 to minus 2. So that is important, otherwise you are in a region of parameters that you make a lot of mathematics, but then it's completely useless. So you must remember this is very small. The electron is almost zero, the mass of the. The muon is a bit bigger, but still is much smaller than. I mean, this is in fact is due to the fact that the mass of the particle is generated by the heat and so on. So it's like the symmetries are true if m is equal to 0. So this is reflected to the fact that the fermions are almost without mass. You cannot assume a big mass. This is important because there are mathematical physics results in which we assume that m is greater than lambda are correct, but it's a bit unclear. Okay, so the starting point, let me skip the definition. Let me go directly to the technique. Okay. So if you integrate the z, you will get a theory. So I put in this Vn now all. So now what I can do, I can integrate the z. Okay. And then of course you integrate the z. Yeah. Very good. Very good. But I'm not able to do that. I just kept from another paper. Just paste it. So that is the script. Yeah. Okay. And then you get it. Okay, you integrate, yes, very different. You integrate that, then this is a Gaussian integral, it's linear, so that's very easy. I mean, this is, everything is finite dimension, so there is no problem, so you get a quartic interaction. Okay. This step is correct because there is m. On the other hand, when you do that, you lose something. I mean, as I will tell you later, I mean, that's a possibility. I think you will lose the fact that there is a decay for large k doing that. But anyway, now, let's do this step. Now we reduce this to this quartic interaction, to this term here. So at the end, this is the basic object which people study in this framework. So this is a Grassmann integration. This is a quartic form. So just to fix ideas, this is something like this. if you want to get rigorous results, you cannot expand the Feynman graph. Because the Feynman graphs are too many. The Feynman graphs are n factorial square. But it's very simple. It's simple as a kernel, because you will see this expression of the kernel. So it is well known that the kernel, if you bound each kernel, you get not bound, but of course it's sensitive to the kernel outside. In my product, it's bound not. So now let me go then. So before speaking about this model, let me tell you some results about our friends. I go in the end, but so what are these Grassmann integrals? So let me recall some basic stuff. So Grassmann integrals are the simplest things that exist in the world, because they are something simply which are complete and commutative, and the integration is simply given by this rule. Depth size 0, depth size 1. So this is the beginning and the end of the theory. So for it's finished, because if you have size square is 0. So any function can be considered in this way, but that's very, very easy. So for instance, depth psi e to the psi is a. So you expand in series, and then you get 1 is 0, psi square is 0, you have on this. Okay. So of course, the point is that when you have more than so the theory of Grassmann integral with only one integral, only one variable is very easy. So let us consider more variables. So if you have more variables, that is a useful formula. The exponential, the psi of psi 8 psi is the sum of all the permutations. It is called a fraction. So you have this fraction. So this is called fraction of 8. And in fact, it is easy to make them. So it's very easy to check this formula. You expand, and then it is non-zero only when you have this permutation of this thing. because you use simply the first rule, the size one. That's what this is the pattern. So if you have two kinds of independent, two kinds of bytes, so you add the plus or minus. Before I have only one star. If you add two kinds for the same height, then you get a determinant. It is also very easy. That also can be checked by this format. Gaussian A to the square is equal to the determinant. So that's our all elementary properties of matrices. And that's the point. I mean, we keep everything finite dimensional, so everything is given by finite dimensional. So there is no mystery, no infinity, nothing, just determinant. So the simplest stuff that exists. Or let me make a small digression. As also yesterday was quoted this result about Ising model. And so for it, the Ising model is a realization of this Grassmann variable. So that is well known, but if you have not seen it, maybe it's nice to see. So this Ising model, which was presented yesterday. So this Ising model, the partition function can, the solution, or at least one of the solution of the Ising model can be simply obtained writing this expectation in terms of Grassmann variable. So in fact, it's even much easier to see it in terms of diners, which is another, I don't know, maybe this definition, I don't know how much is useful, but the Ising model is solved mapping in the Diner model. A Diner model is I don't know if you know what is it. Then the Diner model is pretty easy to use. That's for instance is the partition function for the Diner model. So this Grassmann variable has nothing to do with quantum field theory. Are an object which appears in several places. It appears, for instance, in the solution of the Ising model. In fact, yesterday we have seen the Ising model in two dimensions. The solution of the Ising model in two dimensions is obtained writing each system of functions. And the functions, in fact, are Grassmann, so you can represent the Grassmann variable. So this is the reason why there is a relation between the Ising model in two dimensions and the quantum Ising model, because they are the same method in fairness. So but that's just algebra. I mean, so that is a very easy exercise. Now, maybe there's no time, but I want just to tell you that you don't know the Grassmann variables are a basic object appearing everywhere. It's nothing to do with quantum theory. It's an object. It's a complicated way to write. When there is no interaction, it's a way to write determinant or pattern, nothing more. Nothing. Okay. Okay, but let's. So the point is that when you have the interaction, so maybe no. Okay. Oh, yes, please. Okay. So you have to remember at the moment you have to remember only this first line. The second no one used. It is used in the Ising model, but it's not nice. No one likes this pattern. Everyone, it's much more complicated to complicate pattern. Everyone likes this determinant. Okay. So it's better, so this pattern are not, no one likes. So it's better to consider this case here in which the quadratic form in which you get a determinant. Okay. If you add another index to this fairness, then you will get the more familiar determinant. But in the Ising model, you have the pattern. In fact, but when you want to compute that, it's better to consider the square of the function. So it's determinant. Anyway, so just remember this. Okay. So maybe it could be even. Okay. Of course, if n is equal to 1, it's obvious. Okay, I don't know how much this is obvious. found that you can that the only term the main side, so you have B or B or B to the man. So okay, but that is the free theory. So let's go here. So this is what I wrote there. So instead of calling it A, I call it G minus 1. So that would be the propagator. Propagator is just the covariance. Okay? So the first line is that. So one likes to write in this way. So look, this is interesting. If you make this Grassmann integral, you get G minus 1. If you get the Gaussian, you get G. So there is a sign. This is what is called supersymmetry. Property. So if you make the product, you get 1. Okay, so that's it. That looks similar, but there is a minus 1. So the rules of this Grassmann integral are very similar, but this is you get the inverse. But when you consider the measure is not a real measure because these are Grassmann variables. Formally, it's very similar because then you get G, which is exactly the same thing you would get if you consider the z bar divided by the normalization. Okay. So formally, it's like an integral. If you forget the sign and you consider it, so okay, this is what it is. Okay. Of course, which are the problem? This is completely trivial. What is not simple is now that we consider a large number of fields. So for instance, if you go in momentum space, then now you see this is a finite dimensional. So suppose that this C hat has the formal Fourier transform. So K would be a discrete index. We have periodic boundary conditions. So K would be of the form 2 pi n over L. So you have a product. K is discrete and is up to 1 over A, which is the proposal. Okay? So in fact, so no one likes this formula, and the physics is often written in this way. So, if you don't agree wrong, I don't know what you work with. The limit of that. But this is a big matrix. So there is no deep mathematics. It's just an L by L matrix. Okay. So now what we have to do? I mean, the theory of free case would be just to integrate that is doable because it's determinant and so on. So which are the formulas? So for instance, the expectation of product of this psi is a determinant. Okay? The determinant can be this determinant, if you want, you can represent explicitly. So it's the sum of the permutation with the sign with the product of the G. So it has to be. Okay, so these are the rules. Okay, they are on the end. So all this is non-interactive. So what happens? when they consider this kind of objects, which are the general forms. Okay. Then, of course, you can expand in V, then you get this expectation. So suppose that you have this for simplicity, it's a bit more complicated. You see that already sigma, the bar. Let's consider something, the basic example. So you will get the product of this quartic term. Then apparently there is no problem. You insert this here, then you use that, and then you expand. Okay? So what do we get in here? We can do that, and then okay. Now maybe this is already said. Okay, but let me just make this more remarkable. This is not analytic. It is, of course, you have one variable, it's of course analytical. So already the zero-dimensional case show you that you can have a, so that's a very important point. You can have an analytic in lambda, while it's impossible to have an analytic in lambda for bosons. So that is a crucial remark. Fermions are analytic. So the power series expansion is correct in this case. You already see from this case. Just this is, if you want physically, Pauli principle. So anyway, so let's just consider. So let's try to do that. So which kind of bounds we can get? So of course, we will get a very bad bound. Which one? I mean, this is possible. Everything is finite, so we can bound it. So these are well-defined objects, so we can get a bound. So we use this determinant. And so the very naive bound is n factorial square times the maximum of the G, or the infinity norm, times the volume, because we have to integrate. So it's a very bad bound. This is the bound. N factorial, G infinity to 2n, volume to the n. It's finite, but it's not very complicated. But it's fine. Okay. So of course, this is several. So this is even more pessimistic. So this, and then sorry, I forgot the lambda here. There's a lambda here now. The lambda here. Lambda is the coupling. Okay, simple, right? So the terms of the determinant are, the matrix are 2n by 2n. So you have 2n to 2n terms. I take the G infinity norm and the volume because I have some. Okay, not very bad. So there is a lot of problems. So now all the story is we want to kill the factorial. We want to kill the volume to the n, and then the G infinity when you remove the cutoff is infinite. So it has all possible problems. In reality, the norm of the G is typically infinite. And factorial is not very nice for convergence, and the volume of course is infinite. So let's see. Let's also notice immediately that G infinity has problems. It's ultraviolet problem. It's problems for small x. So typically this G is diverging at coinciding points. Okay, so this is okay. Anyway, this is abstract. Then now we have to consider the real problem and see what we get. The first thing is this is a very well-known trick. Even if yesterday I was discussing with Jan Lewinsky, and they said that they don't. In some cases, you don't use that. Okay, we will see how it's possible because you see here you get this volume, and instead, if I use the truncated expectation, then the volume to the end disappears. Okay, so in other words, you have to take the log. Okay. This is called a linked cluster theorem, which is complicated operator. But with the Grassmann variable, it's completely obvious. It's nothing. It's just a definition. So this is the advantage of considering the linked the Grassmann variable. So this is the definition of truncated expectation, which is the same definition as for probability. Are called in different communities, cumulants, I don't know, truncated expectations, several names, variance, covariance, moments, maybe the moments in probability. Okay. So for instance, if you consider 2, you have x minus x squared. So 3, you have all the possible disconnections. Okay. And then simply, the linked cluster in this formula is obvious because you write the log. So that's the important point is that you want to make the log. The log, you expand the log in series, and then you expand, it's expansion around lambda equal to 0 and lambda to 1 to 0. Okay? So that's very important. So the log, so first lesson, the log is much better. You don't have to integrate the partition function, but you have to integrate the log of the partition function. This is very well known in statistical physics. Because at the end, it's simply due to the fact that the free energy is the log of Z, and the free energy is an extensive quantity. So the log of Z has to go as the volume. So if log of Z goes as the volume, then Z is the exponential of the volume. And then if you expand the exponential of the volume, it's nothing more than that. Okay? So it is well known. Okay, so now we have a better bound. Okay, the bound is a bit better because now you see it's quite easy to see why it's so important, this truncation. Because of course, so maybe in fact I tell you the answer before telling you why it's important, the truncation. Because the truncation allows you to make the integral. Okay, so in this first bound here, we don't make the G infinity norm, so the integrals are left aside and done alone. But if these terms are all connected, then there is a chain of propagation connecting all these volumes, all these coordinates, and then you can use this G to integrate over the coordinates. Okay, so at the end you get a single volume, not to the end. Only one volume, but in fact you have to divide this by the volume because it's extensive. And then you put here the maximum between the G1 norms and the G infinity norms up to 2n times lambda to the n, again divided by n factorial. But this is a single term. Then of course these are again n factorial squared. And so again, this bound for all the terms is n factorial, but at least you have eliminated, so that's a very important point. You eliminated an infinite to the n. Because at the end you want to send n to infinity. Okay. So that is it is not clear. Ask me, but that is a very important point. Okay, so maybe. So maybe I don't know how much you are familiar with the graph, but the graph is not important. Maybe I start with English. But when you want to compute the expectation of this, you have to go to all the expectations for all the possible transactions. Some of the terms will be connected. Cosa invece l'uso si parla grazie meglio cioè vuol dire perché la protezione di per condizioni mentre le onde possono quindi le contatti quindi le onde possono ma sometimes we need to connect to make the traffic go. So we need to follow what the motion of services. So the time of the product the all the customers in fact. And of course that group of 10 are connected to the 10. But if you consider the conflict, then you are only the connected there. Then you can use the connected. If you have integrated then you have voice. You have integrated overall the possible form. Okay? But then it's up to this translation in backward. So this from one interaction to all the other can be done by G1 norm for Quantissima, then it's going to make the volume, then all the other Q you found by the. So that is already a great gain. Because now, you remember, if you don't do that, of course, you lose a lot because but you are doing a very stupid thing. You are expanding the exponential of the volume in, understand? It's like you're expanding the power of the only one volume. On the other hand, this must be so because the free energy is extensive. The free energy is the loss. Okay, so this is called linked cluster theorem in quantum physics. Of course, you have the analog of that for operators, which is much more complicated. For operators, it's much more complicated because we have. So the advantage of Grassmann variable is the perfect anticommutativity. Of course, you can say you get the same result. Yes, you can prove that the series are the same. And then typically what we do is we use Grassmann variables and then we use some analytic continuation to say that it is coinciding with the series obtained with the operator. Okay. Anyway, now we do that. Okay, this is the basic step. So now we get this. But then, okay. So the problem are decreased a bit. So remember that at the beginning, the problem is enormous. So of course, it's difficult to arrive to something finite. So I want just to remember you the point because, I mean, at the beginning, this bound is terrible. You have all possible kind of problems. Yes, a volume to the end, then factorial, and this G infinity norm. So at the moment, we have at least solved this problem. And then all the other problems remain. Because here we don't have the n. But this is a single term. Then we have to sum, to multiply over. So the bound is this. So, and factorials, max, and lambda to the n. It's already something. The volume I eliminate because I divided it. It's correct with the normalization. When you consider the correlations, then it's something similar, which there is one coordinate which is not integrate, then you don't have any volume anymore. So now there are two problems. So we solved this problem of the volume. It's already something. Now there is the problem of the factorial and the problem of the max G1 and G infinity. Oh, so both these things are in real cases. So this is, if they are finite, then it's good, but they are not finite. Okay, so what do you mean? Typically, you, for example, one dimension, the propagator is 1 over x. So now in coordinate space, the divergence of the propagator in x equal to 0 is the ultraviolet event. And the low distance behavior for large x is the infrared behavior. So for example, typically you have something like 1 over x within one dimension. So G1 is not where it is infinite, but also G infinity is infinite is also G1. So now let's go in step. So if you are interested in infrared problem, then you are interested in the large distance behavior. Then you can distinguish two cases, the critical cases and the non-critical cases. The non-critical are gapped or massless. So I use a lot of terms because these things are applied by several fields. So you can say the theory is critical when the K is the power law. One can say that the theory is critical if you want to use the language of the physics. You can say that the theory is massless. Because the mass is the same thing as the difference between the temperature. In the contrast, when you have a gap, you can say the theory is gaps or the theory is the mass. So that's it for this problem of G1. So G1 would be okay, would be a constant which you have exponential decay for large distances. So these are the norms they say. Then the G infinity, if you are instead on the lattice, they are finite because they are connected with the small x behavior. If you are in the continuum, instead, they are. Okay, that's it. So anyway, this is what you get. At the top of everything, we see that we have problems even if these G1 and G infinity are finite, because there is the n factorial. Okay. So now we can do in several steps. There are several problems to solve. We have to eliminate, to fix the problem of the G infinity, and to fix the problem of the norms, which are not finite. So typically, what are called the perturbative renormalization consists in saying, okay, we don't care of the n factorial. Let's get at least finite bounds order by order. Okay? That we don't worry of the sum. This is what is done typically in physics. You compute lowest orders, and then you say, okay, we hope. Or I would take the opposite point of view now. We will just change otherwise. Always the same thing. So let me discuss first the problem of killing the n factorial, and then I come back to the problem of these norms which are not finite. But the problem is to be solved simultaneously. So, lesson: the Feynman graph cannot be really used for Archimedean convergence. So you can believe that I am a fanatic of Feynman graphs. In fact, I am, but they cannot be used. So which is the role of Feynman graph? I tell you, you need Feynman graph for computation. So if you want. But it's just a language. I mean, even for languages, I don't find Feynman graph really convenient. Myself, for instance, when I have to make computation short, I remember in my thesis, I didn't use it because I was always wrong with the convention. So I simply prefer to use big rule and count all the possible combinations. So why we use the Feynman graph? Just for easy. You have a friend and you want to say, I found a problem with this term. It's much easier to say the bubble, the sun, so you understand what you're speaking about. But it's just a language. It's difficult to say I have the contraction of this with that, and that gives me problem. Much better to use this. When I was explaining you, I find it better to make in fact, when Feynman explained the Feynman graph, I think Bohr was shocked and very upset. He said that Feynman didn't understand anything about quantum field theory because he was really shocked. Later, anyway, it's just, for instance, we use quantum Feynman graphs for classical mechanics. It's just a way, it's nothing to do with quantum. It's just a way to represent perturbation. It's nothing deep, in my opinion. Simply an easy way to represent that. That is the point of view. Others have a different point of view. My point of view is simply that there are a way to represent it. Okay. Okay, so how we get convergence? So now we have to use this anticommutativity, as I said. So it's a key property of Grassmann integrals. I think this problem was said by Caianiello in 1956. It was first used by Caianiello in 1985. And in fact, I didn't know about Caianiello, and I read about this name by Copiani, and then I said to Vallavot, I discovered this was done by Caianiello, and Vallavot told me, yes, he was my professor, in fact, in Naples. But I discovered his name through the paper of Copiani. So the Caianiello has this idea, which it said he was the first to say that the fermions are convergent. Because he used the Grama-Damar inequality. So everyone knows what is this Grama inequality. If you have a determinant of a matrix, which has its form with an inner product, then you can bound that with the product of the norm of this F and G. Okay. So why this is interesting? Because if you don't have the n factorial. So that is simply, in its basic form, it's simply the inner product. Like the A vector B, if you can compute the A vector B by the determinant, but then of course A vector B is the modulus A, modulus B, cosine of the angles. So of course, right, if you consider the vector, the external product, you have two vectors, you can write it as a determinant. So it seems that you have 4 terms or n terms and factorial terms. But instead, you can represent the modulus and the angle. So that is the grammar form. So this is the simple idea. So if you apply this in a very naive way, so this slides, I don't know why I do in this way. That's if you don't. This is a very. This I learned this by Vincent Rivasso. It's nice because it's even not. I mean, it's a super basic bound. This is very, very pessimistic. You can consider now n variables. So at the end, you consider the scalar product between the G and the delta, and then you apply that and you get a bound like that. You see, the advantage of this bound is that you don't get the n factorial. But now you have the soup already. So anyway, what is very important is that applying this object is that you don't get that. But a better bound is this one. So for that bound, you don't have to know anything about the G. But all the G is usually this form. Usually, all the propagator in all physical application, you can write as AB in this kind of form. They are Fourier transforms. So you can all remember the G is the integral over K of G hat K. So you can always write in this way. So the bound immediately is this is the ground bound with this assumption. So the bound I'll show you before is the bound. If you even don't have to assume this property. But if with this property, it's a bit better. I think it is. Okay. So for the moment, I will consider this one is easier. But don't. If you look to the slides, you will see that you can even use this bound, even if it's not the form of the scalar. But you can always write in this way. Because of course, if the Fourier transform to make the product consist with this times zeta, then the zeta becomes a delta, and you reconstruct the equation. So. Okay. So now, what we have done? We have eliminated the n factorial, but for the expectations. But we said that the expectations are not good. Okay. So we want to use this idea for the truncated expectation. So this is one of the technical points of this constructed quantitative theory is that I mean up to this point it's everything quite elementary. Now the problem is that it's very easy to bounce by determinants the expectation, but then the truncated expectation is not so easy because it's not obvious because they are not determined, more complicated. So you use what are called cluster expansions, a cluster expansion form which is very easy. So here maybe I can skip. That's something very elementary. You can find in any book how you prove the grammar amount inequality. You start from orthogonal set. If it is orthonormal, it's obvious. If it is not orthonormal but orthogonal, you rescale. If it's not orthonormal, you use Gram-Schmidt and you use it. So that is an elementary proof of this grammar inequality. Okay, then let me arrive to the crucial point. So up to this point, so this is a famous formula. This is Bridges-Butter-Fehrenbusch, which is one possibility. There are others. So this formula, which is the advantage. So this formula is an important formula for, gives you a lot of things. Because it says that if you have the product of theta are monomial, okay? And then this means you can represent this as truncated expectation of graph. Okay, so this truncated expectation can be inside. This is classified as identity. So if you consider expectation of this, you have to consider all the possible factors. Next thing, you consider the truncated one, you have only the connected, but then you have some factors. Now this formula says you that Instead of using the paragraph, we can use the representation. We use the number of the sum of the streams. Here are three. The first is the point above the stream. It's not, these forces are not enough, but are three. Why three are less better than that? Because three have no loop, so the combinatory of three is much better. The number of three is bounded by Taylor formula, that order in factorial, not in factorial square. And so the point is that we want to reduce to three. Sum over three, product of G, so so what says this formula is definitely what that is formula. So exactly by contracting it by using expectation, then the method. When you consider expectations, I consider all the things. But I don't need all the possible things. I need only one line. But I use only one connection to motivate. So in this case, if you have all the possible things, then there is propagator. This propagator G allows you to make the interval. All the coordinates are connected by this. All the other things remain in the same. But if you write it instead of the then you will get all the time. But you don't want to do that if you want to bound the determinant, so in the way to expand the determinant to get the factor. But you want to bound the determinant. One of the things that yes. So then what says this formula is that you have several monomials. This is the truncated expectation. So you have the sum of all the possible trees. You extract the propagators corresponding to the tree. Then what remains is this determinant. This PT is just something boring that you have to introduce some interpolation parameter, but this is a probability measure. The integral of this is 1. So if you bound this determinant by Tn, then this is 1, and then no, unfortunately not. And it's a very complicated set of interpolation parameter. Okay, and so maybe. Okay, so you have done. Okay. So for instance, suppose that there is, I think, the first time by Galois. Suppose that in Copiano and it's something very old, it's something back to the cases, late cases. So now you see, now you have what you want. Suppose that you have 1 over volume to the log to the integral. Then you use for the expectation, you have the sum of the integral. Okay? Now you use that formula. So G is a gram matrix. So the determinant is bounded by Cn. The integral over T, just infinity many, is bounded by 1. Now the sum over x or the integral over x is bounded by the G1 log. Then now you use Cayley formula for bounding the tree, the number of trees. The number of unlabeled trees is bounded by Cn. The conventional class with the vertex is an n factorial. Then at the end you get this bound. So that is very good. So you see, now you have the constant times G1 times lambda to the n. So it is solved the problem of the volume and the problem of the factorial. Okay? So of course, what remains? It remains that G1 is infinite. Okay? So of course, usually in physical, so this G1, the norm of the propagator, is even so maybe you get G1 and G infinite, so you get both. Suppose the G infinite is finite, but then still you have the problem of G1. So the norm of G is not decaying very fast. So G became low. So now this doesn't work for. So this is G, G1 is fine, it's okay. I also think you need also G infinity fine. But in real applications, then you have to then you have to fight with that. So at this point, this is not a remediation group. This is simply gradual. So where the remediation group, remediation group, then so now here, because this one in general is not final. So the idea of remediation group is very simple. Instead of considering all the series, all the integration of the psi, we do it instead. So now, if you come back and finish here, so what is all the point? It's a very natural idea. Okay, so the idea is that I would have done. I'm describing this integration. If I expand this d, okay, but then I would get the propagator G minus 1, so the norm G1 of that. So instead of doing this, I divide into pieces in this way. Now, the integration of a single scale is G infinity, is infinity, and one norms, which is finite. It's very well, it's finite because, of course, you have put an infinite and non-finite cutoff. So on the single scale, it's finite. So the single scale is well defined. The problem now is transferred to the integration of the infinite. But the single scale, the single Wilsonian, the renormalization group step is well defined. So instead of doing some perturbation theory, something very singular, you make a multi-sky analysis, decomposing the singularity and making it a system. So that is the relation group. Other questions or Vieri from your you need both. You need the DDS and the Rambam because yes, you need both. No, it's not. Yes, sorry, I have to repeat them. So, just a second. Not a bit. Okay. So so I repeat. The ground bound allows you to bound the expectation. But if you bound the expectation, then you lose the volume because we have there are two problems. You have it could be finite, would be okay, but then you have also the integral. So if you use the ground bounds for that, you kill the factor. But then when you make the integral of the x, then you have the volume to the end. So you want to keep the connection, but also use the determinant. And then if you use this formula, you keep the connection and then you use the determinants only for that, only for the field. So in a sense, it's like this. You don't want, you need the connection to make it stuff, but you don't want to extract all the possible lines because if you extract all the lines, then you get a factor of 12. So you want to extract the minimal number and screw into the connection. Then for the others, you don't expand, and for that determinant, you need the dropout. No, stop. For instance, Stein Gordon is not okay, so you can use the e to the phi and then you get a subset. Actually for school for both. And then and the they didn't do it before. They used another thing. They used what's called phase center composition, which is another technique. Instead, Garis but of course, you can use this formula. First, Stein Gordon into the E5 can be done. But of course, there are several ways. That is my power. But of course, also for boson, is good only if you have Saint Gordon, because Saint Gordon is exponential at E5, which is bounded. For bosons, but generally you have this large field property. So for bosons, the expansion is not very well defined. So you understand this formula is good if you expand the exponential, but for bosons, it's not a good idea anyway to expand the exponential. So you have to distinguish in the integral of x, the large field, so you have to integrate e to the minus lambda x to the fourth. So it's never a good idea to expand lambda x to the fourth in series when x to the fourth is very large. So you have to distinguish when x is large and x is small. But for fermions, it's bounded, so this formula is enough. For bosons, but for bosons is used for Saint Gordon, because the Saint Gordon is e to the E5